Thanks, Sebastian, and thanks a lot to the organizers for putting this really nice workshop together. And you know, it's particularly great to see a lot of friends for the first time after, last couple of years. And so, today I will take a slightly different view on problem of non-equilibrium dynamics, which is, yeah, let me try. Maybe that's better. Yeah, okay. So where I would really take the tools and way of thinking from the open quantum systems. And as a preview, so typically when we are thinking about many-body dynamics, so we think about the many-body wave function, so how it evolves with the Hamiltonian in time, or as a quantum circuit, and then so we try to make sense of this wave function and then measure, for example, local observables after some time. And really the key quantity, the key property is how much spatial entanglement you have generated in the course of your evolution, and that's related to the complexity of describing this wave function. So things that are not very entangled usually are easy to describe, and vice versa. And today I will do something different. So instead of focusing on this large many-body wave function, I would be thinking about the states of a small subsystem at different moments of time. And then so the way to describe the effect of the rest of the system on the subsystem, really, so that comes from the open quantum system. So you can do it by this influence functional, which I will define in a second. And instead of thinking about complexity of the many-body wave function, I'll be thinking about how difficult it is to encode and describe this influence functional. And this would bring us to this notion of temporal entanglement. And the key idea I'll try to convey that this object can be more compact and it can be easier to describe it compared to the full many-body wave function. So it somehow encodes the complexity of computing local observables. And so first, let me start with the basic idea of the approach. So first of all, over the last several years, people have been studying, so what are the possibilities for highly non-equilibrium dynamics in many-body systems. And so there are two main options. So of course, by far the most prevalent is thermalisation. So your system forgets initial states. There is scrambling of quantum information, and you say colloquially that this system is a good thermal bath for its subsystems, right? Then on the opposite end of the spectrum, we have many-body localization, where in some ways quantum coherence is preserved locally, and you say that this is a bad bath. It cannot thermalize its parts. Then there are other things like pre-thermalization and weaker cadicity breaking, which are somewhere in between. But in a way, I want to take this, this idea of describing a many-body system as a bath in the most literal sense, and that's accomplished using this influence functionals. Right. So this goes back to Feynman and Vernon, who are developing a theory of small quantum systems, for example, a spin interacting with a thermal bath, which they modeled as a bunch of harmonic oscillators. So and then what they did is essentially in the path integral formalism. So let's do Keldysh path integral and then integrate out degrees of freedom in the bath. So here I'm denoting them by capital Q, and then you get a path integral of this form where you have the action of the environment of the bath here. You also have forward and backward trajectory because we are doing Keldysh, and then interaction between the bath and your system enters here. So essentially the trajectory of your system enters as a parameter here in this integral, and that defines the influence functional, which is a functional of the forward and backward trajectory of your system only. And this in general, this functional is non-local in time, so it encodes the memory effects of your bath. And people, so in the context of, for example, dissipative two-level systems, so that has been really a starting point, because then you can, for a bath of harmonic oscillators, you can explicitly compute the influence functional, and then various clever approximations have been developed to describe the dynamics of the system. So there is this classic review. And today, I will not be thinking about oscillators, but instead, for me, the bath would be the many-body system itself. And let me start with a concrete example to illustrate how this works. So let me consider a spin chain, and I will take, a very studied Floquet model periodic quantum circuit for the spin chain, which is the kicked Ising model. So I have kick rotation around X and ZZ interaction, and then also a Z rotation to break integrability. So this model is simple, but it is extremely rich, so you can find different regimes in it. And it is very convenient for our purposes to, what we're going to do is essentially consider, for example, one spin as a system and the rest as an environment. And here automatically, because it is Floquet evolution, we can write the path integral. Path integral is essentially discrete. So I can represent it as this tensor network, where at each node, I'm summing over the intermediate states of my system, which is a spin. And effectively, what we have to do to compute influence functional here is trace out the environment, so all the spins here or here, right? And that's going to give us this tensor that depends on the states, on the state of my, on the trajectory of my system. And you see from, pictorially, it's quite easy to see that one way to accomplish that is to note that you can trace out all the degrees of freedom up to here by applying this large operator, the dual transfer matrix, which is just one slice of the tensor network. With legs, there would be 4 to the power evolution time, dimensional space where it is acting, right? So, and that would give you exactly the influence functional. So one way of looking at it is that you need to solve this eigenvalue equation for the dual transfer matrix. And the solution would be exactly the influence functional. And so I can also view this tensor, so influence functional in this context is this tensor, so I'm going to call it influence matrix because it's become discrete. I can also view it as a fictitious wave function defined on this temporal spin chain, right? So it would be just a wave function where states are different configurations on the forward and backward contour. And okay, so let's see if this, what this could be good for. First of all, so we note that this object has minimal complexity for computing dynamics of local observables, right? Because in working with it, I have discarded a lot of information that is living in the bath, but maybe not relevant for my local observables. And qualitatively, we can expect that there can be cases where this complexity is lower than the full wave function complexity. And the way, one natural way to try to understand it and probe it is to study scaling of temporal entanglement with the evolution time that you're looking at. And in particular, we can expect that if this scaling is favorable, so for example, if there is area law for temporal entanglement, we can describe it efficiently using tensor networks, sort of applying ideas from DMRG and matrix product state and all that very nice technology. And let me start, so to motivate it, so let me start with a few examples of exact solutions, right? So that's always nice to have cases where you really have a closed form understanding of the object you're working with. And first type of exact solution comes actually in this model when you choose particular values of the kick and ZZ interaction. So specifically, if you choose them to be pi over 4, then for any Z field, turns out that you can solve this eigenvalue equation exactly, and the resulting form of the influence functional is extremely simple, so it looks like that. So it's just the product of delta functions of the configuration of the spin on the forward and backward trajectory at every moment of time. So it is a product state. It tells you that essentially your environment is canceling all the phases after each step, right? So therefore we call it perfect dephaser influence matrix. It's a very interesting example of a system that is in general chaotic. So for example, this model would have level repulsion and so on, which however acts as a purely Markovian bus for its subsystems. And this is also, so this point is known to be special, so going back to this works, right, which observed that in this case, the tensor network describing it becomes dual unitary, so it is unitary both in time and in space direction. Yeah.
So at some point you showed something like Caldera-related type structure where you integrate out oscillators. And there, the path is Markovian if you are at high temperature, but it's very non-Markovian at 0 temperature.
Yes.
So here, is there even the notion of temperature, and why is it actually Markovian?
There is, right, that's an excellent question. So there is no notion of temperature because this is a Fouquet problem. So why is it Markovian? Essentially because at these parameters, your circuit is very entangling, right? So whatever state you start from, let's say you started with a spin pointing up. At the next step, it would be maximally entangled with its neighbors, and therefore locally, right, it completely forgot where it started from. So I think that's the intuition.
So it's like infinite temperature.
It is infinite temperature, yeah. But of course not, so what you would see is that not every spin chain which is infinite temperature would have a 0 memory time, right? Because things can, for example, you can have diffusion, right, where things relax slowly. But this is an example of a initially difficult problem in the real space where you have a lot of entanglement that becomes trivial using this representation, right? And that's why I think this is an interesting thing to start from. Now, another regime where you can get exact solutions is when you make this model integrable. So I will use, for now the same model. I'll just now turn off Z field. So then it becomes the standard, model solvable by free fermions. It's an interesting model. So in particular, it has interesting structure of edge modes. So here, if I sketch the phase diagram as a function of J and G, you have 4 regimes where you have, here, this would map to the standard Kitaev chain. So you have a 0 Majorana here. You have a pi Majorana in this part of the phase space. And then you have a coexistence of 0 and pi Majorana over there. In all cases, you can, with a bit of work, you can find the influence matrix and show that it has a form of a BCS-like wave function in the time domain now. So this is now this starts looking similar to the bus of bosons, except now it is free fermions. And so pairing in this BCS wave function, so it is parameterized by this function, so you can relate it to the quasi-particle properties in your model. Most importantly, so what you find is that this pairing in the BCS wave function decays sufficiently fast. In this case, it decays as a sufficiently fast power law in time, such that it is fast enough to expect temporal area law entanglement in this case. And here I'm illustrating it in the few corners of the phase diagram. So I'm going, 4 points in different places here, right? And you see that in all cases, scaling of temporal entanglement with evolution time is actually favorable, so it saturates, and it is an area law. You see also, you see that in some parts, this function that determines correlation, temporal correlations, is actually not decaying, but instead it's oscillating. So that's a consequence of having edge modes. So when you're thinking about this, you know, the kind of bath that your spin chain is, there is an edge mode which is always there, and then you remember that, but that of course does not make it a significantly more complicated object. So that's another, you know, nice thing. So for non-interacting models and a broad range of initial states, actually temporal entanglement obeys area law. So it is a simple, you know, it tells you it is a simple object to encode. Now, a less, you know, more intricate example, integrable model, which is non-interacting. So XXZ, right? XXZ Floquet model, which you can show it's known to be integrable by beta ansatz. And in this case, it is also possible to find some exact solutions for the influence functional for a particular choice of the parameters. And what you find that generally, in this case, you have a little bit more temporal entanglement. You have log t scaling of temporal entanglement. And this also holds not only for those cases where we can get exact solutions, but also we believe it holds more generally, because that we just find numerically for a range of initial states. And overall, so this is rather intuitive. So you expect that if you have ballistic quasiparticles in your model, temporal entanglement would be low, because simply, you know, your system interacts with a quasiparticle, then it flies off, right? It never comes back. So this is quite intuitive. Now, one immediate implication of that is that if the temporal entanglement is low at the integrable points, if you detune from them a little bit, you don't expect it to just jump abruptly. So you expect it to stay relatively low even when you break integrability weakly. And here I'm illustrating that by taking the same model, but now turning on a weak Z field. And so I'm showing the evolution of temporal entanglement as a function of time for different values of this integrability breaking perturbation. And you see that actually, again, so I'm showing it for 4, you know, parts in this phase diagram of the kicked Ising model, and you see that there is some rich behavior, but what is important is that temporal entanglement always shows sublinear growth, which is also pretty slow. So it tells you, yeah.
What is your plotting with the state?
What am I choosing as a state?
No, you take the state. What is the quantity that you plot? Is it like half system entropy?
This is maximum, yeah. So usually at the half cut, right? Any other questions up to here? Okay, good. So, and intuitively, you expect, so you see here that this favorable scaling of temporal entanglement goes also into the regime where integrability is broken pretty strongly. And, you know, this is quite intuitive because if your system is thermalizing fast, you expect it to have a relatively short memory time and therefore, you know, short temporal correlations. But this is just intuition, so we don't have a formal kind of proof for that, and we don't know actually if this is true generally. And this makes this way of thinking and, you know, this approach useful, for example, if you want to describe thermalisation and transport in strongly interacting systems. So now I am taking a Hamiltonian model, which again has the same ingredients. So this is transversal Ising model with broken integrability at a point where it's believed to be very sort of quickly thermalizing from previous works, and using MPS encoding of the influence matrix, we can get to relatively long times for simulating local observables and also energy diffusion in this model. So that's been one of the challenges in the field. Yeah.
Why did we still HZI in order to break the degeneracy?
To break integrability, yeah. Right. This is very strongly non-integrable, exactly. So this is, I mean, in this paper by Kim, Ikeda, and Hughes, it was chosen as the sort of most chaotic point where things thermalize fast, the TH nicely holds, and so on. So, and, so difference is just, this is linear and this is log, right? This is log to see that it is following diffusion at longer times. But this has been, this is sort of a standing challenge in the field, and there have been various interesting attempts to develop matrix product operator algorithms to get to this hydrodynamic regime using, also time-dependent variational principle. And since, this is probably the minimum amount of information you need for local observables, this might be the way to do it. And as a fun application of this, so let me just show you one slide of how we used it to model a noisy quantum circuit in a recent experiment we did at Google. So generally, you expect that dissipation in your circuit would only make it easier to describe influence functional, because external dissipation shortens the memory time of your system. And indeed, so this is the case. And let me just spend 1 minute flashing this experiment. And then if you want to know more, I'll be more than happy to tell you more. So here we essentially were realizing this same Floquet circuit. So applying series of X rotations and then ZZ interactions between pairs of qubits, and then applying Z rotations. And so our goal was essentially to image the edge modes and then see how they respond to various sources of noise. And so you can do various nice things here. So you can map out how in smaller chains your quasi-particle spectrum changes as you tune this kick parameter. So you can see the gap closing, and then you can see the Majorana edge mode emerging and disappearing and splitting and so on. And you can use that to actually image the wave function. So this is literally the wave function of the Majorana mode up to, let's say, 12 sites or so in a chain of about 45 qubits. And we have used, so in this context, we have used the influence matrix method to describe the behavior of edge modes in the presence of weak dissipation and model the dissipation going on in the device, and that allowed us to get to pretty long times. So, and with that, so let me just tell you about one more application of this way of thinking, which is to quantum impurity models. Right? Of course, quantum impurity models. So this is a classic problem in condensed matter physics, and there, you have what we are talking about from the beginning. So you have an impurity interacting with one or more reservoirs, which are usually assumed to be non-interacting, right? And generally, it is difficult to describe a situation where the system is strongly out of equilibrium. So when you have large voltage difference between the two reservoirs, right, and things like that, describing what happens with a strongly interacting impurity. And here our strategy is essentially as follows. So we use Grassmann path integral to explicitly compute the influence functional of the reservoirs, very much in the same spirit as I showed for the quantizing model, such that we got this quadratic wave function in the temporal domain, right, for each reservoir. We can have 1, 2, or 5. That doesn't make much difference. And then there is a nice algorithm which we had to extend a little bit by Fishman-White to convert this influence matrix, which is Gaussian, into a matrix product state. So there is a sort of algorithmic way to do it. And if this is done successfully, then this is pretty nice, because then you can insert any impurity Hamiltonian you like, and the time observables can be computed efficiently. And so what we have done so far, so we have shown that the scaling of temporal entanglement is indeed favorable. So generally, the influence functional of the non-interacting reservoirs has this quadratic form, where just like for the Characterising model, we relate this kernel to the spectral properties and the initial state of the reservoir. So this is, of course, extremely closely related to the Keldysh-Green's functions. And then what we find that for Fermi C-type initial states, temporal entanglement scales logarithmically in time. So here it's shown for a particular simple model of a reservoir, simple tight binding model. And then for a bunch of other initial states, which are at finite temperature, product state, you have area law temporal entanglement. And what this tells you, and probably the statement can be made more rigorous, is that many non-equilibrium impurity problems can be efficiently solved, right? And so there has been previous work, showing that equilibrium impurity problems can be solved efficiently, right? But this gives you a practical way how to also solve a bunch of non-equilibrium impurity problems. And nice thing is really that, complexity here is determined by how difficult it is to encode the properties of reservoirs and not the impurity, because impurity is usually a small system, such that if you've done that, you've solved every non-equilibrium impurity problem. So, and hopefully we'll have more news on the implementation of that. And with that, so let me stop here. So I described to you this view of quantum many-body dynamics problems, where you view the system as a bath, and then you work with its influence functional. And the complexity of it is determined by temporal entanglement. And in many cases, so as I try to argue, you can compress it very efficiently using tensor networks. And among applications, so I've mentioned high equilibrium dynamics in unitary and dissipative circuits, quantum transport, impurity models, and then one more thing that I did not have time to talk about is quantum control. But that gives you also a very natural language for quantum control if you want to torture part of your system at different moments of time. This is probably the right language for it. And so I will stop here. Thanks for your attention.